Okay, here we've got a question in context. Now, because we're in the booklet, we know it's going to be a normal approximation to a Poisson, but the question itself doesn't mention either. It says we've got a quiet road with cars passing at the rate of 1 every 2.5 minutes, and I want the probability that 3 cars pass in a 10-minute period. So I'm counting events, cars, in a 10-minute period, which is a fixed time. So if we're counting events in a fixed time or space, and as long as the events are occurring randomly, independently, and at a constant average rate, then it will be Poisson. So I have to make all of those assumptions, that it's independent, that it's at a constant average rate. But if it is, then in part A, my exact distribution, okay, is, well, it's going to be a Poisson. Now, the original mean in a 2.5 minute period, we've got a 1 car on average passing every 2.5 minutes. I've got to scale my mean, so I've now got a 10-minute period. Remember, Poisson from S2, we learned that we can just adjust Poisson means without penalty. So in 10 minutes, it ought to be 4 times the mean. So if it's 1 in 2.5 minutes, that means it's an average of 4 every 10 minutes. So I've got an exact distribution being Poisson with mean 4, so my lambda is 4. So I've got to work out the probability that exactly 3 cars pass. So I want the probability that x equals 3. So my diagram of outcomes, I need values near 3, 2, 3, 4. Okay, I want 3, but I can't have 2, I can't have 4, can't have everything else. So my box that captures the ticks does that, and my other box does that. Okay. Now, although the topic is normal approximation to binomial, at the top of the page here, it doesn't say use a distributional approximation. So never, ever, ever leap to a distributional approximation unless approximation has been mentioned. So we're just going to do the normal thing. So I've got a big box, which is the probability that x is less than or equal to 3, and I need to take away the probability that x is less than or equal to 2. So I now, on my calculator, need to go into Poisson CD mode. So that's second page, Poisson CD, which is number 3, and I need to make sure my x is 3 for the first one, and my mean, my lambda was 4, so I'm going to get, first probability is going to be 0.43347 minus second probability, when x is 2, is going to be 0.23810, and when I subtract those two probabilities and round to 4 significant figures, and I get 0.1954. So that's part A. Part B now does mention use a distributional approximation. So I had my exact distribution here, but oh no, that's changed, hasn't it? I've now got a 1 hour period. Okay, so how many 2.5 minutes are there in 1 hour? Well, like I'm going from 10 minutes to an hour. That's 6 times as long. So I've now got a Poisson with a mean 6 times as big. So my exact distribution is x twiddling a Poisson. So it's 24 is the average number in an hour. Okay, so I've got a lambda is 24. Okay, which is quite large. Good enough. So since lambda is large, I can now set up an approximate distribution. Okay, but in between this, I need to set up the correct parameters. The approximate distribution, the only approximation I can do to a Poisson is a normal. So I need a mean, and mean for a Poisson is just lambda, so that's 24. And the other thing I know about a Poisson is the variance is lambda, which is also 24. So my normal distribution has mean 24 and variance 24, but let's clarify, mu equals 24, sigma squared equals 24, but sigma is the square root of 24, and I've got to be careful to use that one for my approximate, for my probability. So let's go back at the question. I want no more than 14 cars passing. So I want the probability that x is no more than 14. Okay, so let's just make sure have I got that right. 13, 14, 15. Okay, it's allowed to be 14. It's not allowed to be more than 14, and it can be all of these. So my box would come like that. So my continuity correction is the probability that x is less than 14.5. Okay, so I've done my normal distribution. What value's in the middle? Mean of the distribution u is 24. Okay, I've got the value of 14.5 down here. Okay, quite low. Alright, so I need to work out the probability of being less than that. So therefore I'm going to get a z value. So z equals 14.5 minus the mean 24 divided by sigma, not sigma squared, so that's the square root of 24. Okay, do that on the calculator. There it goes. What's that z? That z is minus 1.9392. That looks right from my diagram, it's negative. So I've got my correct z here, and that needs to be the upper bound. Lower is going to be minus 9999. So here I've set that up with the lower and the upper. So press equals, I get p equals 0.02624. So that's my probability that I needed. I'm done on part B. And I've just got to do part C. Part C says, explain why we couldn't use a distributional approximation in part A. So this is the normal question turned around. Why didn't it tell me to use a distributional approximation here? Remember, you only use a distributional approximation if it tells you to. But why didn't they tell you to? Well, because I can do a distributional approximation when lambda is large, but in part A, lambda is 4, which is small. So that's what I have to say for part C. So part C, lambda equals 4 is small. So the normal approximation is not appropriate. Okay, and that finishes this topic. Okay, actually, just one final thing. Going back to the beginning of the topic, where you go from a binomial to a Poisson. I'll just do this in a random space. When you go from a binomial, and you think, ooh, n is large and p is small, and you go from that to a Poisson, it could be if n was something like 1,000, okay, and p was 0.05, then you'd think, okay, n is large, p is small, so I'd go to a Poisson. And the mean for that Poisson would be n times p, which is 1,000 times 0.05 is what, 50? That's what I meant it to be. So if that's true, then I've got a Poisson with a large mean, which would actually go to a normal. Okay, a normal with mean 50. So in fact, if np is very large, even after you said that n is large and p is small, it might be that your binomial can be approximated by a Poisson, which could be approximated by a normal. If you see that happening, then you can sometimes go from binomial direct to normal. Okay, so if you get a Poisson approximation, but the mean of that is very large, okay, then it may be the question intends you to do a normal approximation. Now, in the old days, when you had to get your Poisson probabilities from tables, then you'd tell that this was happening because this value of lambda here wouldn't be in the table. Here are the Poisson tables from your formula book, which you never use because you have a calculator. And the different values of lambda, we can see values of lambda here, and the biggest value of lambda that these tables allow you to look at is 15. So if you did do an approximation and lambda was anything bigger than 15, you wouldn't have been able to actually use the tables. You'd have had to say, okay, lambda's larger than 15, so it's larger to do a normal approximation to that. So when we do past paper questions, we just need to look out for questions where the Poisson approximation would have been appropriate, but the lambda is so large that it makes sense to go on to a normal if you want to get the right answer in the mark scheme. I think they have to be very careful about the way they word exams now, that the calculators will allow you to work out Poissons even when this table doesn't work.